On the board, I've got some multi-step synthesis practice for us. The first one, I can see this being solved in 4 steps using the chemistry that we know. The other 3, I see them being solved in 3 steps. And remember that I consider any reaction that requires an aqueous workup to just be 1 step. The reaction and the aqueous workup are separate steps. So I want you guys to spend some time on that. Before you do, though, can we review the tips for retrosynthesis or multi-step synthesis? What are things that help you solve these synthetic problems?
Try going backwards.
Yep. Work forward and backwards. Sometimes you see a starting material and you know exactly what you need to do to it. You need to do elimination, you need to do oxidation, you need to do Grignard addition, you need to do acylation on an aromatic ring. Sometimes it's not obvious what you need to do. So if you see a final product, you can say, I know a functional group in there that I can form. Let me show the formation of that functional group, and maybe that gives me a better idea of how to work forward. What else? I feel like I should put this on the test. Just kidding. It's not a learning objective. One of them, the basics. A skill you learned how to do in kindergarten, maybe 1st grade. Maybe before kindergarten? Count. You learned how to paint.
Counting your carbons.
Count your carbons. In fact, this is the one that I say first. Count your carbons, or I think it's a little bit better to phrase it as map your carbons, so that you know, am I forming any carbon-carbon bonds? Because if I am, I might need to do acylation or alkylation to an aromatic ring. I might need to do a Grignard or acyl addition with an organometallic. There's not a lot of carbon-carbon bond formations, so if there are carbon-carbon bonds forming, we should look for that. And the last one, the last tip I have you guys try to think about. I know this one kind of feels the most vague, but it's brainstorm. And that usually comes down to, I see the functional groups in my starting material, and I know what reactions I can do with them. And I see functional groups in my products, and I know what reactions I can do to get them. This kind of works the same with forward and backwards, but I think brainstorming comes before that, so that you can actually have a list of reactions that you can use to work forward and backwards. Let's solve one of these together before you guys... Are you guys interested in just spending time on your own solving these? Or do you want to solve them together? Yeah, I think let's at least solve this first one together. Matt, can you talk to me about mapping carbons from the starting material to the product? Do you notice anything that changes? Adds on an alcohol.
Or removes alcohol.
Okay, it does not remove an alcohol. It removes an OH, but that OH is not an alcohol. What functional group is this? carboxylic acid. Very important to be able to recognize what functional group it is. Otherwise, the list of reactions open to you kind of falls away. If you try to apply reactions for alcohols there, none of them would work, but reactions for carboxylic acids would. I'm going to disagree with you, though, that nothing changes. We can start by mapping these 4 carbons on the starting material to the product. I think you would agree that this carbon 1 is this methyl group, all the way to carbon 4 being this carbonyl. And look what I get at the final product. I get a 5th carbon that was not there in the product. So to say that we just lose the OH isn't true. We gain a carbon. Now this sets me up for my brainstorming. I need to be able to do reactions with carboxylic acids. And we can add to that list in a little bit. But I also need to do some carbon-carbon bond formation. And at the end of it, I need to make sure that I have a ketone. So we can say ketone synthesis. Unit 4 gets a lot more into reactions with carboxylic acids. But have we seen any reactions so far that have a carboxylic acid starting material? What do you find, Sam?
I'm looking at, but I don't know if it's right, where we reduce it.
Okay, reduction of carboxylic acids.
Which filter I'm looking for.
And what does that form?
It takes off.
Oh, actually, let's take a step back. Since Caesar's looking for it, what section did you find it in, or what class of reactions?
In preparing alcohols, kind of. It's
So-
like reaction 8, if you remember them.
I did. Well, I was looking at it.
That's why the numbers are more helpful than just my little arrows, right?
So like reducing it to alcohol. That's where it was. Okay.
Did you find it?
Well, I found some stuff, but I don't know.
Carboxylic acid starting material
Yeah.
to what substituted alcohol?
Primarily.
To a primary alcohol. Are there other reactions with carboxylic acids that we've seen?
Acyl substitution.
Actually, carboxylic acid was at the bottom of acyl substitution and said, oh no, I'm sorry, you're right. I was thinking acyl addition with Grignards, sorry.
Yeah.
Yeah, acyl substitution with alcohols, right?
Yeah, that's an ester.
Acyl substitution to an ester. Okay, well, esters would have more carbons than a carboxylic acid. But I think you guys agree that the carbons would be separated. I wouldn't be able to form a bond between 4 and 5. I would have this oxygen in between it. So I think that's all the reactions we saw so far with carboxylic acids. And I don't think that acyl substitution is going to work. So in our brainstorming, I think we have a good idea of how to work forward from this reaction. I think we're going to need to start with reduction.
Wasn't there a reaction where you could reduce? Well, it was not necessarily like with the carboxylic acid, but you could reduce the OH to like a aldehyde. Can I do it if it's part of a carboxylic acid group?
Okay, hang on. Taking the carboxylic acid to an aldehyde,
Well, yeah, I know you can't. But
there is a reagent called dibol that is a selective, moderate, not even moderate, a selective reducing agent.
Right.
And it will take reagents like this down just one oxidation step. It will reduce it once to an aldehyde. We'll look at that more in the aldehyde section
Did we do something like that though? That's what I was looking for.
We have the benzylic reaction, which takes aldehydes and ketones and reduces them to alkane.
Oh, yeah.
And then we have sodium borohydride, NaBH4, which only reduces the aldehyde, the ketone, the acid chloride, and LAH, which reduces all of them. Maybe you're thinking of...
Yeah, we reduce the whole thing to an alcohol.
Yeah. So this, for now, the only reaction we've seen is taking a carboxylic acid all the way to an alcohol. Now I'm gonna start working forward on that because that's really the only reaction we've seen that's gonna help us progress somewhere. I think you guys would agree that if we did acyl substitution to an ester, I mean, we're just gonna get an ester that needs to be reduced anyways. So what are my reagents for reducing carboxylic acid? First, LAH. Second, H3O+, that acid workup. All right, mapping my carbons, I'm not gaining or losing any, and the alcohol that forms is on carbon 4. All right, let's keep brainstorming. How do I synthesize a ketone? How many different reactions have we seen where the end product is a ketone functional group? This one might be a little bit challenging, but given the fact that this multi-step synthesis is in this section, there's probably reactions we've seen recently that give this.
The oxidation of alcohols.
Good. Oxidation of what alcohol? Oops.
I think a dye substitution.
Di-substituted would be language more for like alkenes. I think what you're looking for is secondary.
Okay, sure.
Well, this actually gives me another brainstorming idea. If this one pans out, I'm going to need to figure out how to synthesize a secondary alcohol, because I don't have a secondary alcohol at the moment. So this actually tells me, if it works out, I've got some more brainstorming to do. Are there other ways that you guys have seen to make ketones? I can rephrase that. There are other ways that you guys have seen to make ketones.
With the medicinal alcohols.
Yeah. Although, you know what? Should we look into that a little bit more? Periodic cleavage. Vicinal diols. Because I think I mentioned, I don't know that I've ever seen it forming a ketone. Hey, there it is. It'll form a ketone. Good. All right.
I'm guessing that's not it.
So we could, though. We could do oxidative cleavage
Oh,
of a vicinal diol. But I am going to say, I need to add carbons in this synthesis. I'm not sure that I'm too excited about cleaving carbons during an oxidative cleavage. Does that seem fair? There are some other ways that we've seen to form ketones. And these actually go beyond the chapter on alcohols. So this, as we prepare for the midterm next week, I think this is a good opportunity for us to think about our OCHEM1 reactions as well. So I'll give you guys a hint. There's another cleavage reaction that we learned in OChem 1 that can produce a ketone. And there's an alkyne reaction that can produce a ketone. It's ringing bells.
The mercurial something.
Good, yeah. Oxymercuration of an alkyne. Okay, as I think about oxymercuration of an alkyne, I know I need to form a carbon-carbon bond, and I could use the acetylide alkyne anion. I could do acyl addition maybe, and I could add a carbon-carbon bond, or maybe I do substitution with acetylide. But that's going to add 2 carbons, and I want to only add 1 carbon. So I don't think adding 2 carbons with the alkyne is going to work. And then there's ozonolysis. Ozonolysis is another oxidative cleavage. So once again, I don't think it'll be great for us to do any cleavage reactions because that's going to make us lose carbons, not gain any. And I don't think it'll be meaningful for us to add an alkyne and then hydrate the alkyne with oxymercuration because that's going to add too many carbons. So that tells me my best bet is probably to get here by the oxidation of a secondary alcohol. What carbon is the secondary alcohol on in the starting material? Yeah, carbon 4. Sorry, I didn't mean starting material, but in the precursor. Because that carbonyl carbon is my alcohol carbon. Caesar, what are some reagents I could use here? Sorry?
Oh, to use there? You can
No, water won't work.
not because it's chlorinated. You gotta think
It's okay.
yeah, I know.
Yeah. I'm gonna.
Will it be basic? Will it be something basic, right? No? Yeah,
Well, I mean, no, it won't be basic.
I can't think through these, man. That's what I'm saying. Like, I don't remember stuff. I'm remembering all these reactions.
I know.
Ugh.
That's why I'm telling you guys the best way to get familiar is to spend time in those reactions. Caitlin, what about you? What's a good reagent we could use here to take this secondary alcohol to a ketone? PCC works. Do you remember what PCC stands for?
No.
Pyridinium chlorochromate. Very similar to chromic acid. It's still acidic conditions. It still has a chromium reagent. PCC, though, more moderate. Chromic acid, more aggressive. I can't use chromic acid here. Is that right? That's wrong. I can use chromic acid here.
You can use both, right?
I could use PCC or chromic acid. And since PCC is easier to write out,
Can you remind me what PCC is?
PCC, Sam?
It's a mild oxidizer.
Or you're looking for the initials, the acronym.
Yeah, whatever.
Pyridinium chlorochromate. Mild oxidizer. Think about these oxidizers needing acidic conditions to help run the reaction. Pyridinium, not as good of an acid. Chromic acid, much better acid.
So, from alcohol to go to a ketone, you need acidic conditions?
Sure, but we're not showing the acidic conditions as H3O plus. But you're right that it is not basic conditions.
Right, because, well, the way I'm trying to think about it, so if you have the oxygen, and you take you're taking the hydrogen out, so you're donating electrons, right? So these accepting electrons.
Well, it's a little confusing. Technically, electrons are being stolen from carbon-4.
Okay.
Its hydrogen is being removed. And it's accepting electrons from the oxygen to make the double bond. I mean, technically everything is a Lewis acid-base reaction.
So don't think about it like that.
No.
Okay. Just remember PCC.
If you guys are interested in the mechanism of how these work, it's not always hard to find them. That's fair. And keep looking. Find as many ways as you can. If you look at this mechanism, though, Caesar, you'll see that there are Lewis acids and bases all over the place, and some Bronsted-Lowry acids and bases. So in this oxidation, you can see carbon is forced to share its electrons with the oxygen to form the double bond. And in this bond, carbon owns the electrons. In being oxidized, it's losing those electrons because now oxygen owns them. Is that a mechanism you want to learn? I could put it on the exam. Yeah. All right, so here we are. We have worked forward and backwards. We started with reduction to a primary alcohol, and we ended with oxidation of a secondary alcohol to a ketone. Now we need to try and figure out, how do I go from a primary alcohol to a secondary alcohol? Keeping in mind that this is a 4-step synthesis, so there's going to be 2 more steps and 1 intermediate in between here. Well, we still have not brainstormed carbon-carbon bond formation. So, give me the rundown again. How many different ways are there to do carbon-carbon bond formations?
30.
Yeah. EAS, alkylation, acylation. Relevant here? Far from it. No aromatic ring. Then there's the alkyne anion, the acetylide ion, which we already ruled out is not going to be useful because, well, yeah, but we said there were reactions we could do with the alkyne. No, the alkyne wasn't effective for us because it adds too many carbons. It's going to add 2 carbons to my molecule, not just 1. I need just 1. What else? Yeah, our organometallics. Acyl addition. Wait, acyl addition? I don't have an acyl group. So, this tells me that I need 1 more step in this synthesis, which is I have to make an acyl group. Remind me what an acyl group is? CO double bond, one of our carbonyls. That's an acyl group. Could I not have just done acyl addition there? Could I take an organometallic, add at carbon 4, and just already be here? Why not?
Because
What if I add methyl,
It'll react with the alcohol, take the H, and then it won't be a
not an
grignard
alcohol?
H anymore. Or the carboxylic acid OH group. Sorry.
Not an alcohol, but you're right. The Grignard is such a strong base that the Grignard will simply deprotonate the carboxylic acid. The Grignard will not be able to run acyl addition. So I can't do acyl addition from my starting material. I also can't do acyl addition here, but I need carbon 4 to be an acyl group so that I can have carbon 5 attack it and turn it into this secondary alcohol. So I just want to point this out. What reaction will help me form a secondary alcohol by acyl addition? I'm sorry?
Secondary alcohol, also we're doing the
Yeah. I want to make a secondary alcohol by using acyl addition.
You said that is the Grignard.
Yep, we're looking at a Grignard or organolithium. We're not looking at a cuprate. Where do you think I would direct you in your notes to look for this reaction? Would it be in the preparation of alcohols or in the reaction with alcohols section? Reactions with alcohols means alcohol is the starting material. Formation, preparation of alcohols. This is the preparation of an alcohol. Similar to this, reduction of the carboxylic acid, that was preparation of alcohols. Acyl addition, preparation of alcohols. What functional group did we say goes through acyl addition? All right, now you went and found it in your notes, maybe, or you have an idea. I can show you how to solve it without needing to go back to your notes. I need to add carbon 5 somewhere along this way. Carbon 5 is going to bond to carbon 4. So the bond I want to form is between 4 and 5. 4 is the alcohol carbon. And with acyl addition, the alcohol carbon is always the carbonyl carbon. Well, in this case, the carbonyl carbon is primary. So it's not a ketone. It's an aldehyde. So if you go back and find it in your notes, we said aldehydes go through acyl addition to form a secondary alcohol. Aldehydes are a primary carbonyl group. And aldehydes are not acidic, like the carboxylic acid or the alcohol. So they react with the Grignard the way we want. Help me fill in the last two reagents. What reagent takes my primary alcohol to an aldehyde? PCC. And I cannot use chromic acid for this, correct? Primary alcohol and chromic acid gives what functional group? Carboxylic acid. If I used chromic acid, it would just reverse my first step. PCC limits the oxidation to one step gives me the aldehyde. Caitlin, what can I use in the last step?
In the last, like the one that's empty,
Yeah, sorry.
the, bring your reagent.
How to spell it out for me?
So I did CH3 MgCl for one, and then 2 the H3O test.
How did you know it was CH3?
Because there was one CH group in there.
Yeah, that's carbon 5. And carbon 5 is not connected to anything else. So I just need it to be methyl. If carbon 5 had been a benzene ring, pH, I would have just made this pH. If carbon 5 had been an 18 carbon chain, I would have just made this an 18 carbon chain molecule. And you chose MgCl. Is MgBr wrong? Is MgI wrong? Is Li wrong? Is CH3 2CuLi wrong? Yeah, the cuprate won't do the acyl addition. But this one will. This is great. Here's the deal about multi-step synthesis. You guys are going to get a chance to do it again on your unit test this weekend. You're going to have a roadmap synthesis where you're just filling in reagents and filling in missing products. And you're also going to have a multi-step synthesis. So you'll get a chance this weekend to push yourself and put your skills to the test. But on the exam, the multi-step synthesis is, I try to grade it or assign it points for how many steps there are, or the steps and the intermediates. That way, even if you have a step that doesn't add to your synthesis, you can still get points for showing the right product out of that step. And our multi-step syntheses are going to be 2 to 4 steps long. You'll have 2 options, so you will not have to do just whichever one I give you. You'll have a choice between 2 of them. And they'll be the same number of points, so the same number of steps. You guys can see that this 4-step synthesis took us a while to brainstorm and work out. You don't have that kind of time on the exam next week, which means you've got to push yourself this weekend. Figure out how to hone in on those reactions, look for those changes, identify what functional groups are present, how they can change. Okay. It also means I've seen a lot of students that just entirely skip the multi-step synthesis. They leave it blank, which I don't understand because I do give partial credit. So putting something, you've got a better chance of getting points than putting nothing. But those students get to the exam and they feel overwhelmed by answering all the questions and trying to develop this skill for the first time. Do you guys want some time to try and work on the others by yourselves? I'm happy to go through the next one with you guys, but I'm going to do a lot less of the talking, a lot less of the probing, a lot less of the directing. So I'd be happy to facilitate y'all's discussion. That's not my native tongue. Your guys' discussion. That sounds so much more right to me. And by the way, if you are someone who feels like multi-step synthesis comes easy to them, you'll learn by teaching. By trying to work with other people and get them to think like you do, you start to recognize why you have that thinking process. You have to justify it. You can't just say, it's a gut feeling. Even if it is. Alright, you guys mind if I erase this list that we made? I want to give you guys some time to at least try getting some brainstorming down for this, or some answers. And while you work on that, I'm going to put up a roadmap. And I want to work from there. Any questions I can help answer?
I'm stuck on this one.
Okay.
Yeah, I don't know, I've looked and I'm not 100% sure where I should start.
What does your brainstorming tool do?
I know I need to do the reaction, or at least I think about that the alcohol that it goes and makes that ester connection there with like maybe
What groups are needed for that?
I need alcohol, but then I need, I don't know, an O? No, not an O. I don't need, I don't know.
We actually just had it on our
Did we?
list earlier, reactions with carboxylic acids. We only had two, reduction of a carboxylic acid and a acyl substitution.
Mhm.
So you need to have a carboxylic acid at that position. Have you mapped your carbons? Are you sure which?
That's what also what I was trying to figure out. I thought that this one would have to come over here, wouldn't it?
Yeah, I mean, how the molecule wiggles around is a little up to us, but
Uh-huh.
like, let's talk about that carbon right there.
Mhm.
Where is that in the molecule?
This one?
Mm-hmm.
It's gotta be here, right?
I don't know.
No.
Maybe try mapping them.
I did, that's what I'm struggling with.
Try
There is the
try just going one direction and then
Okay.
trying to find that same direction in the product.
Okay.
And if one direction doesn't work, try going the other direction. Maybe that'll be more helpful. This is great.
This one, from what I'm thinking.
So I see you tried mapping carbon 1 here to carbon 1 here. Do you agree?
Yes.
Carbon 1 is bonded to 2, 3, 4, 5. Carbon 1 is bonded to 2, 3, 4, 5. And carbon methyl. There's no methyl carbon over here.
This is.
We can say if this is 1, and this is 1, 1 to 2 to 3 to 4 to 5, 1 to 2 to 3 to 4 to 5. Hang on, did I draw it wrong? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. I did draw it wrong.
Because I'm getting so confused.
Someone?
I've got a typo.
Oh, this one?
Okay, cool.
Yeah.
Because I'm like, this doesn't work.
I'm going through all my brain and I can't get it.
I'm like, it's gonna
Okay, alright, now we go.
Okay.
Wasn't that such a small change? I'm sorry.
No, not
I'm
possible.
stressed.
I missed a CH2 group in there.
It's like
No, it wasn't. It was not designed to be possible.
Okay.
My
The
apologies.
trick.
My apologies.
I was like, normally I can see it really like easily, but I'm like, I don't understand. Okay, let's see if I can figure this one
Okay, good. Sorry. This is not the functional group we want to make this functional group. So you know the name of this? No, it's not. It's close. It sounds like ether. And ether, though, is just ROR. And what you've got is carbonyl OR. So you've got the ether oxygen and her sister, ester. Mhm.
Okay, because you basically want this to attack. No. Oh, okay. I gotta rebuild this thing.
Yeah. Mm-hmm. So you've mapped them appropriately.
Yeah.
And remember, it should take you about 3 steps.
I'm just trying to figure out how I can get this alcohol and that the same. I don't know.
Well, you know what a precursor needs to be to this, right? We've only seen one way to synthesize an ester.
Yeah.
So you should be able to break it apart and show what forms it.
Yeah.
Take the bond you want to make, which is this, break it,
Okay.
and have the 2 functional groups that need to be there, the carboxylic acid and the alcohol. And now you've predicted the final step. Any questions? Okay, well, your mapping looks good. Other than the fact that carbon 2 here has an alcohol group and a bond to O. Carbon 2 here doesn't. And then kind of the same thing, carbon 6 here has a bond to an OH. Carbon 6 here has no bonds to O. So what if we kept this mapping the same? Or let's keep this mapping the same, 1 through 6. But we flipped the mapping here. 1, 2, 3, 4, 5, 6. That would put a bond from 1 to an oxygen, 1 to an oxygen. 5 to an oxygen. And then 6 would just be this metal. So by flipping it, our numbering here, we can actually see how each of these carbons is present. I don't need to do any acyl addition. I shouldn't be doing any cleavage, anything like that. And then you gotta look back through your notes, or you could even use the internet as your resource and say, what reactions have we seen that form an ester functional group? And there's a lot of reactions we saw with alcohols, right? And so knowing how to go forward is not super easy. But if I can figure out what this came from, that will narrow down my options for what I can do going forward. Mm-hmm. Yeah, that's it. I don't think you're. Sorry.
No,
No, numbering works. Sorry, your numbering doesn't make a lot of sense, but your numbering works. And it's just weird that you've got like 1 through 5 and 6. But there is nothing wrong with it. You have mapped them appropriately.
Okay.
I maybe wouldn't buy your map, but it's mapped.
But the numbers match.
That's right.
So.
I've actually had a student who said, numbering the carbons doesn't make sense to me because as soon as I see that, I start thinking about nomenclature. And I'm like, oh, okay. So she would actually go in with like stars, triangles, squares, X's, and she would more visually map them with symbols.
Yeah.
But that kind of gave her the same process, you know, put a star at this carbon and a star at that carbon to map them as the same carbon.
Right? It could be both. Not just the one.
100%. However, an aldehyde and alcohol do not react to form an ester. They don't. We'll actually learn in Unit 4 that aldehydes and alcohols do go through reactions.
Is there a way to make a ester from something, or do I have to like close it and then?
Yeah, no. There is a way to make an ester. We've only seen one way to make an ester. And I'll tell you it's in the reactions with alcohols. There it is. Peaceful substitution
Oh.
to esters.
So I'll make an ester and then
Well, when you make the ester, it will close itself.
oh, I don't have to actually
The making of the ester closes the ring
wait, can it go like this?
because the alcohol and the carboxylic acid were on different molecules. This is an intermolecular reaction, and the one that we're looking at is an intramolecular reaction.
Okay, so I will need to add another alcohol with the rest because I need to add carbon. I need to add carbons.
You don't need to add carbons. You don't need to add alcohols. Everything you need is on the molecule already.
So it's just H+.
You don't have a carboxylic acid yet.
No, but I'm going to and then just H++, right?
You need to make a carboxylic acid without making a ketone.
So,
Well, you erased a little bit more than you needed to. PCC won't work for us to make a carboxylic acid. What would we need? Good. Good. And the only change that it does down here, it turns your aldehyde. It still makes a ketone. This one. This is a secondary alcohol. It can only be turned into a ketone. Primary can be turned into aldehyde or carboxylic acid. So this is the issue. It's going to do both.
And to take this one.
Yeah.
Where did I get this one?
Yes, great job. You're really close here, but it should be in a BH4. And I'd like to have you show it with an aqueous follow-up, just like our LAH reaction. Nice, that's it. Yes, that's how I envisioned it happening as well. You could also just skip this step. And then you could also skip this step because of that. But those are the steps that I would have gotten in. Sam, the route that you're on with this one is gonna get you to the final product,
This one?
but in more steps than 3. Just so you know.
Okay.
You can get there for sure. It'll just take you a little bit of extra steps. Oh, actually, maybe not. No, I think you maybe could get there. I think you could get there.
Okay, let me think about it.
Yeah. So we got PCC, an oxidizer. But PCC is going to remove hydrogens from the oxygen and carbon. It's going to create double bonds between them. What it won't do is create any carbon-carbon bonds. So it's not going to take these atoms and loop them together. Yeah. PCC would give us just a straight carbon chain, an aldehyde and a ketone. To make an ester, we need an alcohol to react with a carboxylic acid. Carbon 1 is the carbon of the carboxylic acid. Carbon 5 is the carbon of the alcohol. So if we redrew this, and then erased this bond between carbonyl and oxygen, we now have the carboxylic acid and the alcohol. And those are the groups we've got that need to be there to form this. And now we can see that we need to get carboxylic acid and still maintain an alcohol. That's going to require 2 steps from us. Caitlin, do you want to put a solution up here? Or maybe this one. Yeah. Caesar, do you want to put a solution up?
Which one?
The one on the left.
I don't know if I got it right. I don't think I got it right.
You only drop this. I don't know that this works. So Br2 in light, that's a radical reaction. Where is the most stable radical position? I'm not really sure. There's no most substituted carbon. I'm not sure how the alcohol affects the radical.
Maybe I need to go on with EAS or NAS reaction.
There's no aromatic ring.
I don't know.
But you found this way to form an epoxide. Halohydrin, NaH, gives me the epoxide. Is there another starting material and a different reagent I could use?
Yeah.
Like what?
Can't remember. I used to like.
So there is another functional group we could have at the precursor. Maybe that functional group can also be formed from this alcohol. Alright.
Would it be illegal if I just made one of these a double bond like this?
No, it wouldn't be illegal,
Okay.
but then it wouldn't rearrange.
Because
That sp2 hybridized carbon, there's going to be a carbocation here,
yeah.
and it's actually just going to be resonance delocalized across both of the end carbons, and it's going to look exactly the same.
Okay.
So you wouldn't go through a hydride shift.
So I could.
Mhm.
Okay, let's see if I did.
But I was actually going to say, well, I think you're adding too many carbons by making it. Okay, that works too, but that does the same thing that your first one did. Still rearranges.
But it's a double bond.
Yeah, I don't know that it would work. That sp2 carbocation is not stable. It's not easy to form.
So is this the stuff that's lacking then?
No, I mean I think that you can get it from that step.
Will I have to
It's
do,
actually
like,
once you-
elimination to this?
Mm-mm. Not necessarily. Well, you can't because you don't have any
Yeah.
functionality. But you could put some functionality on there.
I could do can I do the light anti-Markovnikov thing?
What Br2
Oh, yeah.
Br2 in light is actually not anti-Markovnikov because that's an addition reaction and it needs an yeah. There you go.
Okay, but
So that's what you need.
is the anti.
No.
Oh,
And
that is what I need.
the anti-Markovnikov has an alkene, and then it adds HBr with H2O2, and it adds the HBr anti-Markovnikov. That's the appropriate use of that term.
This one's the benzylic.
That's the benzylic and the allylic position.
Which would be great.
Yes,
Well,
it
I did
would.
this initially, but I didn't think that would work.
Yeah.
Oh,
Well, not with this reagent.
No, yeah, I know, but from here I can get to there. That's what I had the first time.
Mm-hmm. What reagent takes us from the alkene to the epoxide?
Just a bunch of things. If there are some with the RCOOH thing.
Just that RCO3H. Or the favorite one is NCPDA.
Okay, so none of that's on there.
I believe you can get to that final product in one step.
Oh, okay. I think I could just do this thing.
Yes.
Okay. Yay.
Yep.
Just do that.
No. This won't work.
Yeah.
This is just going to give you acid-base equilibrium. How do we eliminate the alcohol?
That's it.
Acid. Good. Go put that one up on the board when you're done.
Okay. H2SO4 would be good enough.
That's perfect. Yep. Sam, when you're done, you want to put that one up on the board too?
Yeah. with it? Like that?
No,
No.
no, actually what you're running is a simple SN1
Oh,
synthesis of the ether.
okay. So it just works.
That's it. Oh. Matt, you want to take a look at the roadmap and see if there's anything that you recognize that maybe you can fill in, whether it's a reagent that you recognize or a product. Mm-hmm.
You see, I had this version and then annotating it there.
That's how it does it, yep. That's one of our ways. Good work. Good job, Sam. Okay, so just to review, in this first synthesis, we take a ketone to an epoxide. If we were to map our carbons, what I would say is carbon 1 of the ketone and an adjacent carbon to the ketone need to go through the chemistry. I don't want to totally get rid of my carbon-oxygen bond at carbon 1. I just want to change how it exists. I can make an epoxide by one of two ways. I can do epoxidation with a peroxy acid, or I can do elimination with a halohydrin. If I had a halohydrin here, I would need to get a halohydrin from this starting material. And that is a little bit trickier to do because the halohydrin, we saw synthesizing the halohydrin from an alkene addition. So I still have to get from this to an alkene. And if I'm already going to have an alkene, I might as well just do epoxidation. So then how do I get an alkene from this starting material? Well, there's not a lot of things I can do from here. I can do reduction, I can do acyl addition. Acyl addition, not desirable, adds too many carbons. Reduction to the alcohol allows me to do dehydration, acid catalyzed dehydration to the alkene, and then epoxidation. Up here, I've got these two alcohols and I want to make an ester. Now, mapping proved a little bit challenging given that I had the wrong carbon chain at the start. But one of the more challenging things about mapping is which carbon should go where. My eye is drawn to this methyl group. It's the only methyl group in the molecule. So here's my CH3, here's my CH3. Carbon 1, carbon 2 is bonded to an oxygen. 3, 4, 5, 6 is also bonded to an oxygen. So the only way that we've seen to make an ester is to make that carbonyl to O bond. So down here, we've got a carboxylic acid and an alcohol. This is intramolecular, meaning I don't need to add a carboxylic acid and an alcohol together. Just as long as they're both on the same molecule, they'll react in acidic conditions. So I've got my carboxylic acid and my alcohol, and I can see here that the alcohol, the secondary alcohol, doesn't go through a change. But the primary alcohol needs to be fully oxidized to a carboxylic acid. There's only one way to fully oxidize a primary alcohol to a carboxylic acid, and that's with chromic acid or potassium permanganate. We need a strong oxidizer here, which means inevitably my ketone is going to be oxidized as well. But I can't afford to have a ketone because I need to have an alcohol there. So now I can selectively reduce, keep the carboxylic acid, reduce the ketone using sodium borohydride. And in the last one, there is more than one correct way to solve this, So I want to show you guys another synthetic route that works for this as well. The route that Sam chose, same number of steps, starts with alkylation using isopropyl chloride. She could have also used 1-chloropropane, and it would have rearranged to give me this isopropyl chloride, or isopropyl group. Then she did benzylic halogenation. Recognize that the bromine here will not go on any position of the ring. It doesn't have the catalyst that's needed for EAS. Instead, it's going to form a radical at the most stable position, this position right next to the ring. Now she's got the carbon group that she wants in the final product, but not the right functional group. But we know that we can make ethers by doing substitution. At this tertiary position, I want to go through SN1. So she uses methanol, a weak base, weak nucleophile, helps facilitate SN1 to that final product. Here's the other route. I could take my benzene ring and I could start with acylation. This helps to get 2 of the 3 carbons plus a carbon bonded to oxygen right at the benzylic position. I need to have another carbon. I need to have another methyl group. So I can add something like CH3Li or CH3MgBr. This will give me acyl addition. And if I don't follow it up with an aqueous workup and I leave it as the alkoxide, I can take that alkoxide directly to CH3I or CH3Br or CH3Cl, and I can form my ether by Williamson ether synthesis. So we used 2 different routes to make the ether, one substitution and one another substitution, but in the opposite direction. And if you don't like this, if you don't like having to skip the aqueous workup, because I know some students, they only think about doing it in an aqueous workup, we could follow this up with the aqueous workup. It just gives me OH, in which case I would need to deprotonate it again. So I could start with NaH to deprotonate and CH3I to do the substitution. It's basically adding a protonation and following it with deprotonation. And if I have those 2 steps right next to each other, I might as well just not do either of them. All right. Does anybody want to try and fill in anything on the roadmap? You don't need to add everything. We can fill this in piece by piece. And maybe I should ask, does the roadmap make more sense? Is it easier to fill in than solving a multi-step synthesis?
I think for me, it's not easier. It's easier to get partial. Like if I didn't know exactly what I could do get partial because I know I can do some of them because you have some intermediate. So even if you don't know how to get there, you can get there. But to me, synthesis, there's more options. So like my brain goes through them better, I guess.
Oh, so this pigeonholes you.
Yeah.
There's one right answer.
Yeah.
And this makes you feel more free.
Yeah.
Interesting. You're right. I do like this about a roadmap. If you can't solve this step, you might still be able to solve all of this.
Mm-hmm.
There's no reason knowing the answer at one part is limited by knowing the answer at another part. Yeah.
Like
give you a little,
does give
a little word bank.
Yeah.
Do you know what? That's really interesting. Oh, I know. I give you a cheat sheet so you can make your own word bank, you know? You could really have part of your cheat sheet that says like common generic reagents. You could have LAH, NABH4, PCC, CrO3H2SO4, RMGBr, RLI, R2CULI. And then you don't have to waste space with specific molecules, but you can use just generic things. And then you could just use that as a word bank and say, what am I going to use? Because quite honestly, if I was going to give you a word bank, I'd put so many molecules on there. Molecules that will not be useful in any way. Because I can't just hand it to you. I have to make you rule out things that are wrong, too. I'd have like 2 right answers and 12 wrong. One thing that I want to point out about this roadmap, all my roadmaps are a little bit different. Sometimes you'll see something like this where you have a reagent to predict, and then you have to do it again without really knowing what change has happened. But sometimes you'll get this. I mean, think about what that is. That's a multi-step synthesis. You're right, acyl addition is in there. But that is a multi-step synthesis right there built into the roadmap. Meaning you can't solve it without being able to work forward and backwards. And then there are these other places where they're not really multi-step synthesis, but they are a little bit more challenging. One thing I do try to do in my roadmaps is have an equal number of reagents that you have to fill in and an equal number of products that you have to fill in. Also, by the way, I mean, if this doesn't feel as productive for you guys, if there are questions you want to be asking or problems you want to be going over, we can do that. This is just, like, this is the expectation for you guys of what you'll need to be able to do. So let me know if you have anything specific you want to look at.
Can I make a granular from there?
You can make a grenade from there. Do you want to add anything up there?
I think I got it wrong.
I just did the first one.
Oh wait,
It's a 1.
same reaction, never mind.
It's all one. Yep, that's the roadmap. How do you take isopropyl chloride and get down to this beast?
From the top right one to the alkene. So we need to, I'm guessing we need
Oh, I didn't add the box, but you're right. Thank you.
I don't know about this part. I don't know if that would do.
Oh,
No,
no.
that's what I thought. I was like, I don't know.
Sorry, I didn't read it.
But up to there, if I take out that part, it's right. I knew that wasn't, I just had to put something.
Mm-hmm. Yeah, good job. So you just got to figure out what reagent,
What would do that, yeah.
what reagent to add there. You know, I have as our learning objectives, they're kind of based on like what the unit quiz questions are. Our learning objectives are preparation of alcohols, preparation of ethers and epoxides, preparation of organometallics, reactions of alcohols, reactions of organometallics, reactions with epoxides, and reaction flowchart and multi-subsynthesis, which sounds really dull, but very, very summed up for all the time we spent on those reactions, don't you think? And they all bleed together. How do you prepare an alcohol? You can use organometallics. It's a little, maybe not specific enough. Oh. Yeah, that's it. There you go. Hang on, wait, what?
Oh, just from here on this, I'm not sure yet.
Oh, you didn't get this reagent.
Oh, that.
And this is not the correct way to interpret the structure. It says PHLI, but you've got PHCH2LI. There you go. This is correct, but it wasn't correct based on what you'd actually drawn. There were, yeah, there you go. Oh, and recognize that it says 1, 2. 1 phenolithium, 2 aqueous workup. I know that's just copying it down. You wouldn't lose points because it would have been on there. But I want you to, when you see those acyl additions, you should have an aqueous workup second. Mm-hmm. That looks good. And yeah, you got it. So it's just there. Mm-hmm. And I don't know if this was super clear, but this step forms 2 products, and we're just not using this one.
So that's a specific thing you can use the HIO for on there.
There you go.
Again?
That's. What else would you want to use?
That's the only thing I thought I could use.
That is the only thing you.
Why does that form CHO2?
Well,
Oh, sorry.
what it does is it takes a vicinal diol
Mhm.
and it cleaves the 2 carbons of the vicinal diol, which is going to give you this and this.
Okay.
And then it turns them into aldehydes or ketones. Mm-hmm. That stare down that you had with the board.
I was like, I don't freaking know what this is, but
This is a little easier than that, I would say.
Caitlin says opposite.
Oh.
The thing is this is easier if I don't have all my reactions in my head, So this one, I like it, but having it on a paper makes it harder. But when they're all just in there floating around, it's easier. Because we did a lot of complicated synthesis in my last class, and I ended up enjoying it. But I also had all my reactions memorized.
Yes, exactly.
Yeah.
And I'm telling you guys, you shouldn't memorize them. You should get familiar with them. I feel like memorizing really limits you to only thinking about a specific example reaction. But being familiar means you know how to apply the reaction in a lot of different settings. And your cheat sheet, and my best advice would be to have examples, but to make those examples as generic as possible so that you can just apply them.
I feel like I have a mix on my sheet right now of like, I feel like my alkenes and alkynes, it's like I can just have them out and it's easy to spot. But with alcohols, I'm starting to just write like a sentence, like how to reduce primary or like how to this, just like very generic phrases. And
Sure.
that's
You don't have a. Oh, good. So the generic phrasing is helping
yeah, just
without
like,
needing to have a example.
and I can like draw like how to do a triple bond to this or you know.
Yeah, and if your cheat sheet has just a little box that says preparation of alcohols, then you know where to go when you need to form an alcohol, and you've got all of those little sentences saying all the different ways you can do it. It's a good point. And we talked about how to prepare primary alcohols, and we can do that from alkene additions, but we can also do that from reduction of a few carbonyls or acyl addition to formaldehyde. So if you've got a section on primary or preparation of alcohols, how do you want to format all of the different reactions? Do you want to format them by oxidation, acyl addition, reduction, or do you want to format them by the substitution of the alcohol that you have? And maybe you leave out reactions that you know. If there's alkene addition reactions that you know, leave them out. There's a lot of right ways to do it. Oh, and I forgot to tell you guys, because I told my OCHEM 1 class after you yesterday, don't forget that this cheat sheet is not an advantage. It is a risk. You are taking a risk by having it and feeling dependent on it, or thinking that it's going to give you all the answers when it really doesn't. So mitigate that risk by making it early and making it often. Should we fill some things in? Anybody? Not too much. Save some for the rest.
Okay.
I just had a weird flashback. Anytime we'd choke on water growing up, whether it's like swimming in the pool or in the bath, my dad would always say, save some for the fishes. Like I was choking on the water because I wanted to have it for myself.
You're being greedy.
Yeah, exactly. Good job. Matt, do you know that reagent that takes you from that last product Caitlin drew to the final product? I'll give you a hint. It's on the board somewhere else. So look at the functional group that is changing. Look at the functional group that's formed. You got it. Yep. Do you want to? I'll put it in for you. You got it. Check mark for today. Anybody else?
Before I have to do stuff with the stuff I don't. So my brain's not working.
Absolutely.
Like I can't think about some of this anymore.
Do you guys have any sort of class group messaging? group chat?
You know,
Yeah.
I have her phone number. That's it.
Every class is different, and I don't try to force social interactions. But it can be really helpful to have. It can be really helpful to have like a class group chat, because then when homework problems come up, somebody's going to have a question on it. Somebody's going to have an answer, and then everybody else that has that question has an answer too. People that have good ways of studying, they can add in their study tips.
This is what I wasn't sure about.
We did.
Same.
What we did in my last class,
This is
is-
one of them.
it really does help becoming
Yes.
familiar with the reactions and then like practicing synthesis, at least for me, because then like I memorized them, but then I learned how to apply them in synthesis. So we would create synthesis problems for each other and practice them, because that's the best way to learn how to apply the things that I memorized.
That is what I was gonna. That's where I was going with this. If you guys have a group chat, you can come up with synthesis problems on your own, where now you have to try and figure out, how can I piece these reactions together? And start small. Take a 4-carbon chain and see what you can do, or just have a 6-membered ring and see what happens. You try to think about the reactions, you create a synthesis, and then you pull out the middle stuff and you send it to your friends or classmates, and you see, you like get more examples of applying them. And I know we're coming down to the wire, but there's going to be a lot of synthesis throughout the rest of the semester. So I wanted to actually spend some time today doing that, having you guys come up with your own synthesis problems. And I feel like, well, we just didn't get a lot done. Well, I mean, we did do a lot, and you guys, I think, learned about how to dive into your notes, what you're going to need to prepare for the exam next week.
So don't we need to know the sulfites and stuff too?
We don't need to.
Well, for homework.
If it's on the homework, I only imagine it's like one problem.
Okay.
Is it on the homework?
I haven't done the 18.
Oh, okay. But you're noticing that the chapter says sulfides?
Yeah, that's
We won't be going into the sulfide reactions because they're too hard? No, just because I'd rather us focus on ethers and stuff like that.
Okay.
Sulfides do some pretty cool stuff. I think you guys know that disulfide bonds in DNA and in protein polymers, very cool things. The disulfide bonds are responsible for the texture of your hair. I can't remember exactly what it is. More disulfide bonds, curlier hair. Less disulfide bonds, less curly hair. And that's because you get these two polymers, two proteins that are linked to each other by a sulfide bond. And there are organic reagents that can do the disulfide synthesis and the disulfide reduction. And like that's it. So if you're trying to make the odors that skunks put out, disulfide is important. Sulfide groups are important. But working with sulfur is really stinky. And there's, it's just not something that I thought we should explore this semester. So it might be on the name, but you won't see it on the homework. You won't see it on the tests. So my encouragement to you, if you want to, come up with your own synthesis problems. That alone is going to help you try to think through the reaction types. Start connecting how these reactions build onto each other. And then send them to people and say, do you want to try this? Do you have one you want me to try? If you try this, are there things that I'm doing wrong? Are there like little mistakes that don't work in my synthesis? Can be really useful. That's pretty much our time for today. And I'm rooting for you guys. Remember that you are not, I am not trying to trick you on your unit test this weekend. I'm not trying to trick you on the midterm next week. But there's there's a lot going on.
I don't see it.
I don't know how many times I said it. Yes, a unit test this weekend.
Hey, it's easy to like get like single-minded on there's a midterm,
Midterm,
and then you just forget everything else you have to do. I get it.
Do you guys know where we are meeting for the midterm? Here,
Oh,
right here.
Okay, I was like, this is a trick question.
Do you know what time we're meeting for the midterm?
Normal time.
8 a.m.
Okay.
The exam will start at 8:05, and you have 90 minutes, and that takes us right through the end of the class period. So there'll be 5 minutes for like wiggle room, 5 minutes for getting set up, and then 90 minutes to test. Right here. All right? Have a good weekend, guys.
Yeah.
Happy studying.
I'm gonna have a great weekend.